Hello everyone, and welcome to Live from the Lab. This is the show where we look at different technologies that Bruker has developed to help scientists discover the world around us. Today's topic is SPARC Optical Emission Spectroscopy, sometimes called SPARC OES for short. Now, before joining Bruker, I actually worked at a foundry where we used SPARC OES in order to check our alloy compositions. Fairly easy technique. We just took the sample, ground it down a little bit to make sure the surface was flat, stuck it on the machine, press a button, and get your answer. Now, to dive a little bit more in depth, we're going to talk today from some of our colleagues over in Karlsruhe, Germany. We're going to see a demonstration. And then if you have any questions, make sure to type them into the chat box, and we will get to those at the end after the lab segment. So with that, let's go on and talk to one of my colleagues to get a little bit more in-depth info on this technique. I'm now joined by my colleague Peter from Karlsruhe. Hello, Peter.
Hello, John. Nice to meet you.
So Peter is a specialist in this technique of SPARC optical emission spectroscopy. Could you give us maybe a brief understanding of what actually happens in one of these experiments?
Yeah, that's quite easy because optical emission spectroscopy is also referenced to as AES, atomic emission spectroscopy. So what you really do, and that's similar to what you do in ICP OES, is you atomize a sample. These atoms get excited to a higher electronic state, and when these electrons fall back to the electronic ground state, they emit a characteristic light. That's a so-called emission line. Yeah? And for each element, there are several hundred or thousands emission lines. So this spectra, the emission spectra, is really line rich. If you compare to XRF, where you have only a few lines, here in OES you have way more. And the other difference compared to XRF, for example, is that OES is dealing with the valence, with the outer valence electrons of the atoms, not with the inner ones. And we usually do not create ions. So we do not remove the electrons completely, even not the valence electrons. So that is why you can refer to this also as atomic emission spectroscopy. And here with SPARC OES, we use an electric spark as source of atomization, excitation of the generation of the atoms.
So once you have then this optical spectrum, what do you do with it? How do you get to the answer?
Yeah, you know already that a specific line is representing the amount of the element in this material. So what we do is we're measuring the intensity of this line, and we calibrate then the intensity against a calibration curve against the concentration in this material. And the initial curve is derived by comparing it to certified reference material.
Okay. So now let's focus a little bit on that sample. So you mentioned that we're actually going to kind of spark the sample. So I'd imagine it has some requirements on the type of samples that can be used.
Yeah, it has requirements, and because of the excitation source, the spark has something to do with electricity. There's one requirement that the sample must be electrical conductive, and it must be massive. So a powder or liquid will usually not work. So it must be a rather massive, conductive material. And when we think over the materials, we end up with metals to 90+%.
Now, is there any special technique that has to be applied to the surface? Do we need to smooth it? Can it be, or what goes kind of into preparing a specimen for this technique?
Yeah, once you have prepared a sample, maybe you take this out of the liquid mold of a steel or aluminum and put it in the mold and remove it. Then the sample preparation is normally quite easy. You just grind it, or for the softer materials, you mill it. And you do not need to polish. polish is in the end, maybe you see here little scratches on the material. Yeah, that is ideal. So if you would have it smooth like a mirror, it can happen that the spark that we shoot on the sample is just reflected somewhere else, and that would create a non-energetic discharge. That's nothing what we want. The normal grinding with the, let's say, 80 grit paper is enough. In the end, don't touch it, because that would create contaminations from hands and so on. That is the only requirement that we have.
So now the technique sounds fairly industrial in nature. Is that where we're seeing the majority of applications?
Yeah, you're absolutely right. That is the vast majority of applications, industrial, also industrial research, because there are still some vendors that are creating new alloys and developing them, but it's only more than 99%, I think, have an industrial background. Yeah.
And what different steel, or what different, I should say, metal industries do we see? Is this only a steel technique, or is it used for other metals?
No, it's general metals, let's say. And in OES, you have maybe something I need to add. OES is matrix based. And that's also one difference to XRF. The other would be it's very superior in terms of light element detections and the adhesible LODs. The other is that OES is matrix based, and we don't measure the matrix element itself. This is calculated by 100%. So you measure, for example, in steel, the matrix element present in more than 50% is iron. So we measure all other elements, let's say 40 or 42, including traces and so on, and the rest is iron. But we don't measure the iron concentration itself, because the lines would be too intense and oversaturated.
So which part of the periodic table are we kind of looking at? Like, how low can we go? Is it a low-high thing, or is it a certain element?
You usually go, sorry, I didn't answer the question before. You usually have 10 usual matrices. You have iron, aluminium, copper. Then you have cobalt and nickel. They complete somewhat the iron base. But then you have tin, zinc, lead, titanium, and manganese.
Okay.
Magnesium, sorry. Magnesium have also as well. That should be 10. And then there are requests, for example, for precious metal bases. So we did for the Magellan, we have a gold and a silver base. And maybe there also, and that's maybe the answer to the next question. Yeah, OES requires samples, the availability of samples to do the calibration curve. So if somebody comes with a request, say, give me a tungsten matrix or whatever, but if we cannot buy, or if CRMs are not available on the market, OES cannot do this, because we do a comparison, against the CRM in the end. It's not an absolute light intensity measurement. We always need to compare against the standard.
So it sounds a lot from that perspective that part of the expertise in the technique, of course, is constructing the equipment and having the right software, but it sounds like there's a lot of application knowledge and methodology there too.
That's right, and that's also important when it comes to trace analysis, because OES can really go down to a sub-ppm level, up to a certain height of concentration. And this height of concentration in OES is usually limited by the availability of CRMs and of standards. So if, for example, we can only get on the market the CRM for lead that goes up to 30%, we cannot go to 90% lead. And in this regard, XRF is beneficial, because XRF gets better and more flexible on the high range end, and on let's say the heavy elements, of course.
So then it sounds like in terms of elemental technique, it would be really beneficial actually for a lot of labs have access to both the XRF technique and OES technique. Huh?
they have, where OES is still the workhorse for the metal analysis, and XRF is more for the raw material in certain processes, like the coke in the steel plant, or slag analysis also in the steel, or raw material in other processes, or in metal processing companies, or the backup maybe for an OES system. But the real workload on the metal analysis part, that is usually put on the OES in the industrial environment, because here the benefits, time, money, so it's cheap, it's easy to maintain, it's fast, and it has a low cost of ownership. So that is what makes 90% of the metal analysis in this industrial environment.
All right, so thank you for the great explanations here, Peter. And what we're going to do next now is we're actually going to see some of the scientists in the lab show us how this technique works. They're going to give a demo of a few of the different instruments. And everybody out there, if while you're watching it, please make sure to type in any questions that you have, and we will get to them after the lab demo. So thanks again, Peter.
Thank you, John. Thank you for a nice discussion that we had.
All right, and off to the lab.
Okay.
Hi, welcome to Application Lab. My name is Thiago Souza. I'm here together with Okan Celik today. We are both application scientists for optical emission spectroscopy here at Pruka. And today we're going to be showing you a little bit what we do here in our lab and about some of our instruments here. To start with, we have a Q4 Polo here. Okan, can you please explain a little bit more about the Q4 Polo?
The Q4 Polo is the latest addition to our OES spectrometry line, and it's a benchtop, small benchtop system with CCD detectors inside. We will also later on talk about the PMT systems, and you will see how they differ. But we will also analyze some samples on both units, and we will start with analyzing the cast iron sample on the Polo now.
Yeah, so cast iron is basically alloy of iron and carbon, and with high carbon. So we have, starting from 2.14% carbon is defined as cast iron. Below that is defined as steel. And why is it important to have the chemical composition of a cast iron, for example, or a steel sample?
Yeah, it's actually crucial for a metal manufacturer to know the exact chemical composition of the material they produce, because they want to know what they manufacture is actually what they want to manufacture, and if the chemical concentration of the elements actually meet the specs of that specific grade.
Yeah. And which also define the application in the end, because the main application for cast iron are for diesel engine motors, or
frying pans
that you have in your kitchen.
So yeah,
and also for pipes applications and so on. We basically use OES to define the chemical composition, as Okan explained. And why OES then?
Yeah, because OES is so fast, and when it comes to metal analysis, if you talk about the workload on a metal manufacturing side, it's so high and it has to be quick. So the optical emission spectroscopy is so fast. Under 1 minute, as you can see here, we get the results and we know the chemical composition of our sample. Since time is money, and in the metal manufacturing world, the time is so important, spark optical emission spectroscopy is the right method for the analysis of metal samples.
Yeah, and thank you. And we're gonna do a last burn here on this sample.
Yeah.
And so one really important step that we have for the measurement of a sample with OES is sample preparation. Can you give some examples?
Yeah, when it comes to sample preparation, actually we have two methods. One is for the hard matrices. We grind them with a sandpaper, either 60 or 40 grit.
What are the hard samples?
For the hard samples, could be iron base, could be cobalt, or could be titanium
yeah.
base. Yeah. For the soft material, though, we use machining. So we just machine the sample surface to have a very flat and nice sample surface. That's why we're using milling for aluminum, magnesium, tin, lead, this kind of soft materials.
This is really important, what you just mentioned.
Yeah.
We have different matrices that we work here. So we can work with iron, aluminum, copper, and so on. And one really common question that we get here is, do I need multiple spectrometers to measure different matrices or different alloys? If I need to measure cast iron, or if I need to measure copper, do I need a different one? Can you explain?
No, not really. I mean, in one single instrument, we can have up to 10 different matrices, like the ones we talked about: aluminum, titanium, cobalt, nickel, zinc, tin, lead. So we can all have all these 10 different matrices in one single instrument. So analytically talking, it's so flexible, these CCD systems. Yeah.
And again, is mainly used for quality control and also process control. And when we talk about process control, we are talking about traces. And
Yeah.
for that, we use mainly our Q8 Magellan that we have here. Now on the Q8, since we check already a cast iron sample, we're gonna change the alloy. We're gonna check now an aluminum alloy.
Yeah.
And if it's within the grade that is specified. This one that we have now is one with, let's say, I think it's 0.15% silicon. And, or maybe not, that's why we're gonna find out right now.
And
That's
the
why it's
analysis
important to have
procedure
OES.
is the same. We just press the button once
Yeah.
the sample is ready.
To start, just place the sample in the spark stand, press start, and there you go, you start your measurement.
Yeah. So regardless of the instrument type, either CCD or PMT, the sample preparation and the analysis procedure are exactly the same. Mhm.
Yeah. One important topic when we talk about this instrument, the detector is different.
Yeah.
The detector we have here is?
So it's a PMT. PMT stands for photomultiplier tube. The main advantage of PMT is that it gives us much lower limits of detection, and it's a very stable detection.
Yeah.
So that's why we use. Oops, let's continue
Let's
with
go
the
for
next.
another one.
We use this kind of detectors in this kind of big and robust instruments. And one other difference between the CCD systems and the PMT system is that on the CCD systems, the optical chamber is flushed with argon, whereas the optical chamber on the PMT system is under vacuum.
And this is really important for the transparency here, because we want to analyze traces. And traces, I mean, that is ppm levels. And this is really important to define in each alloy, because define the impurities that you have or inclusions that you may have. And when we're talking about a process control, this is a really important step of it. And we got a second measurement already. We are going for the third one.
Mhm.
What else can we say about
The PMT
the
systems,
PMTs?
like Thiago said, when we need to analyze low alloys where the concentrations are low, or high purity samples like high purity copper, aluminum, etc., there we need the PMTs because of their very low limits of detection. So when we say low, how low are we talking about? So we're talking about single digit ppms, and even some cases sub ppm levels.
Exactly.
Yeah.
That's where it enters the high purity instrument.
Yeah.
So we did the measurements. You can see in your screen that everything is within the specified range with a good reproducibility. And then you can move ahead for the next sample or check another one. If you have to change something, you can also do it. We are coming to the end of our presentation here. Thank you very much. But you're going to join Okan now for the Q&A session. Hope to hear from you soon.
I'll see you in the Q&A session.
Thank
Thank
you.
you.
All right, so now we are here back in the studio with Oken. So hello.
Hello, John.
So Spark OES definitely seems like an intriguing technology for checking things like the alloy composition. Now,
Yes.
we did have a few questions come in, and if anybody else has a question, make sure to type it in, and we will get to it. So the first question was, can you define what massive for a sample is? So I guess, what is the range of sizes that we're talking about here for samples?
Okay, when it comes to size and weight, actually the limiting factor would be the weight rather than the size, because on the Spark template, you can place samples in much bigger than the typical discs that we use in the OES, which are generally 1 inch, 1.5 inch wide. So actually, you can place bigger samples like plates, etc. But again, the limiting factor would be the weight. So depending on the instruments, let's say if you're using a Q4 Polo, the instrument itself weighs around 30-35 kilograms. So if you want to put something even heavier than that, of course, that will affect the balance in the instrument. So there will be some limitation for the weight of the sample. But the size, I mean, the dimensions on the XY dimensions, that shouldn't be a problem as long as you can place it on the Spark template. And if it's too big, of course, somehow you will have to sustain it, right? Support that piece also. Yeah.
Okay, so even if I had, say, like a large gear or a large casting, as long as I can kind of balance it on there and the machine will take the weight, then we're good to go.
Shouldn't be a problem, yeah.
All right, so the next question is actually about a specific instrument. The Q2 Ion was launched in 2010. Is there any new Q2 Ions being launched since?
No, we haven't had any new Q2 Ions. The latest addition is actually the Q4 Polo, our new benchtop OES spectrometer. But the Q2 Ion is still the same Q2 Ion that we had since then. So, yeah, it is the same instrument, and we haven't launched any new version of the Q2 Ion.
All right. All right, next question, still about that Ion. Does it have a touch screen built on top of it?
Okay, yeah. The previous version of the Q2 Ion had that touch screen on top of the instrument, but then, yeah, the company decided to make a design change on it. So they make it much smaller, and we put the PC aside. So, yeah. But the current model, the Q2i, it doesn't have any touch screen. You should use it with an external PC.
Sure. And then the kind of a follow-up question to that, will there be a Q2 Polo? Not a Q4 Polo, but a Q2 Polo.
Q2 Polo, not that I know of. If there will be any successor to Q2 Ion, it will probably have a different name, not Ion, but not Q2 Ion or version 2 or Q2 Polo, because we already have the Q4 Polo, but yeah, not that I know of.
So I guess in terms of that breadth of instrumentation, maybe if you could just briefly just tell us what are the instruments in terms of their size and capabilities. It's just a real quick overview of that.
Yeah, sure. In our product portfolio at the moment, we have 4 OES spectrometers. The Q2 Ion being the smallest one, the benchtop instrument. And you can have up to 5 different matrices on that one. And the step-up model would be the Q4 Polo, our newest OES benchtop spectrometer, which again uses the same type of detection with CCD detectors, just like the Q2 Ion. And after the Q4 Polo, we have the Q4 Tasman. It's even bigger with UV optics, with more chips on it. And in that instrument, we can have up to 10 different matrices. And these are the first three instruments within the product line having the CCD detection. And the last model is the floor standing unit, which is the Q8 Magellan that you should be seeing behind me, 2 of those. they have the PMT detectors, photomultiplier tubes. So the detection system is different, and the interior design is different, etc. But PMTs generally, just like I mentioned in the previous video, in the lab, they give you much better detection limits and precision. So these are the four different instruments that we have in our OES product portfolio.
All right, great. So the next question, is Spark OES a non-destructive technique?
Okay, define destructive. Okay. So, I accept that we destruct a little part of the sample, of the surface. You make those small craters, I would say. But at the end of the day, you do not destruct the totality of the piece, right? You still have your piece, just the surface, and then you can reuse that sample. All you have to do is to machine the surface to have a very flat surface, and then you can reuse it. But it's not like XRF, of course, because on the OES spectrometer, we are bombarding the sample surface with high-frequency sparks, so it has an effect, right? So it doesn't look as shiny as before after the analysis, but you can always reuse the same sample, unless it's so thin, or it's a foil, or something like that.
Yeah, I mean, I've noticed that you can kind of, it leaves that surface, just like you said, a little bumpy, just where it hit it, about a millimeter or so, and then it, a little bit of black discoloration, but I'm sure just a little bit of buffing, especially if you had a casting part or something, then it really wouldn't.
Yeah, you can just grind it, or you can just machine the surface, and then you can go back and use the same sample again. So it's important, especially for CRMs, the certified reference materials. So, they are expensive, and so you can prep your CRM and you can reuse it again and again and again.
So now in terms of, say, like the cost of ownership of one of these instruments over a year, is there really, any consumables? Does it have to have some regular maintenance on it?
When it comes to maintenance, the only thing that you'll be consuming on a daily basis is the argon gas. And by the way, talking about argon, maybe I should point out that the minimum quality that we recommend for our instrument is 4.8, which is 99.998% purity. But if you are doing some trace analysis, especially nitrogen, so on, we would recommend 5.0, which is 99.999% purity. Apart from argon, I think there is nothing else actually that would be consumed on a day-to-day use. We have the wash bottle where the exhaust hose goes into. You can empty that bottle and refill that bottle, but apart from that, and maybe for the sandpaper that you use for grinding might be a consumable, but that's it.
So we had touched a little bit when we were talking with Peter about the idea of X-ray fluorescence, and how that technique, in some ways one could say it's an alternative, but really there's some complementary nature to these. When might an instance be where somebody is interested in, say, having access to both XRF and Spark OES?
It's a discussion. I know that we have had these discussions with many customers in the past also. So XRF, both techniques has pros and cons, right? The XRF is also, it's non-destructive, unlike the OES, of course. But when it comes to analysis of metals, especially in the production of metals, the time is money. You have to be quick and efficient. So that is actually the main reason why the OES is the go-to analysis when it comes to metal analysis. So you have to be quick. In 30 seconds, you have the complete chemical composition of your metal. And there are some parts where we can also use XRF, just like some metal analysis, and also not only the metal analysis. Maybe if you can go back to the beginning of the metal analysis where you get your raw material, there we cannot do anything with the optical emission spectroscopy. There you have to use the XRF because it's about mining industry. There you can use it, the OES not. But yeah, as I said, both has pros and cons, and the main advantage is of the OES is the precision, the limits of detection, and its easiness. Actually, it's so easy to use. All you have to do is to place the sample and push a button, and you get your results within 30-35 seconds.
Okay, so it's really that industrial side of it. If I, like you said,
Yeah.
I just want that simplicity, put the sample, press the button, instantly get a result. That's where this Spark OES technique really lies.
Shines.
All right. Well, thank you to you for joining us for the Q&A. If anybody has any questions, just visit our website, and you can contact us through there, and we will get back to you. But yeah, thanks to you and Tiago and also Peter for joining us today and teaching us all about Spark OES. And until next time, everybody out there, make sure to keep your signals high and your background low.